Dear students, welcome to another online tutorial on principles of communication system. So we are in module 3 and we were discussing about noise. So far we have seen different types of noise and what happens, right, uh, if a noise is passed through an ideal low pass filter or RC integrated, how to find the output power, right? We have seen what is the power spectral density and how to find autocorrelation function or average output power, all those aspects we have seen, right? And in last class, we have seen the concepts like signal to noise ratio, right? We input signal to noise ratio or channel signal to noise ratio and output signal to noise ratio and this noise figure or figure of merit, right? Those aspects were what we have discussed. So from today's session, we will be discussing about actually what noise in AM receivers. Initially, we have to study about noise in AM receivers, and then we'll study about noise in FM receivers, right? So while studying noise in AM receivers, initially, even though we have studied AM like standard AM, then DSBSC, then SSB, like that. So initially, we'll consider DSBSC receiver, right, to analyze the noise. Why? Because that is the simplest of all the cases. Then we'll move on to standard AM, and then as a special case, we'll study SSB. It's not explicitly part of your syllabus. SSB is not a part of your syllabus, but we can't tell, right? So we'll study SSB also. Then we'll study noise in FM receiver, right? So when you analyze the system for noise, what you will be seeing is you'll see what is the SNR input, right? SNR input, or you can input SNR, you can also call actually what channel SNR, right? Both are same, right? Some textbook is using input SNR, some textbook is using channel SNR, right? So our textbook uses the notation channel SNR. Then we'll also find the output SNR at the output. Then we'll find the figure of merit, right? So figure of merit or FOM or gamma, it is nothing but what SNR at output by SNR at input. So this figure of merit is what we'll compare, right? So we'll see DSBSC will have a figure of merit equal to 1, and standard AM, the figure of merit will be less than 1. So noise performance of DSBSC is better compared to standard AM. So those aspects, that's what we have to study. So what do you mean by SNR? It is signal to noise ratio, right? It is nothing but what? It is the signal power divided by noise power, right? So, and we'll be assuming the noise to be an additive wide Gaussian process, right? So we'll assume the noise to be additive wide Gaussian, right? So in last class we have also already seen the system model, right? So in this class we'll continue with that. Initially we'll see the noise in DSBSC receiver. So all of you please take it down along with me. So noise in DSBSC. Right. So before we move ahead with that, so DSBSC signal, if DSBSC signal you are calling it as S of t, it is nothing but what? C of t into M of t. But C of t is carrier and M of t is message, right? So if we assume C of t to be equal to AC cos 2 pi FCT, so it is AC cos 2 pi FCT times M of t, right? So this is our S of t, right? So in order to bring in the influence of the system which we are using, right, we'll add one constant C also. You can, no problem if you assume this constant C to be equal to 1, right? But in order to like bring in the effect of the system, right, maybe it can be the gain which was given by the system, right? So we will be introducing a constant C also. This C is a dimensionless constant. It can be a gain, right? And even if you are not considering that C also, not a problem, right? So but in our discussion we'll consider a C which denotes the effect of system, right? So this is our S of t, right? And if you remember, this S of t right, will have a spectrum like this, right? S of t will have a spectrum like this. This is minus fc and this is plus fc, right? If w is the maximum frequency content in m of t, then the spectrum will span from fc plus w, right? Fc minus w. So the bandwidth is actually what? Total bandwidth bt will be equal to 2w. All these things, you know, right? So this is actually what? S of f, right? This is S of f, right? So and now we'll straight away come to signal model. So how to demodulate a DSBSC system? It's straightforward. We will actually what? We can use a coherent detector, right? We can use a coherent detector, and we have learned a practical coherent detector is actually what goes as receiver. So in this case, we'll be considering an ideal coherent detector. So the system model. So any if whichever be the system or whichever be the modulation scheme for which you are analyzing the noise performance, you should have a system model. So the system model, right? So the modulated signal is S of t, right? And you'll assume the noise to be actually what? Additive white Gaussian noise. So this modulated signal will be contaminated with white Gaussian noise, right? So this is what is, so this will be actually what? At the front end of the receiver, we'll have a band pass filter, right? We'll have a band pass filter. This band pass filter, right, will be designed in such a way that it will allow, right, exactly these frequency range of S of t, that is from plus or minus fc minus w to fc plus w. So this, right, so there is a frequency response of that. We are assuming that to be an ideal band pass filter, right? Ideal band pass filter, which will allow the frequency from fc minus w to fc plus w on positive and negative side, right? So that is your band pass filter. So that is done so that any frequency contents beyond this, right? So the frequency contents of our interest is from fc minus w to fc plus w, right? So any frequency content beyond that will be, right, eliminated by this band pass filter. So it's an ideal band pass filter. Ideal band pass filter. When I say ideal, so the pass band gain we can consider it to be equal to unity, but not a problem, right? Yeah. So we are passing it through a band pass filter. So after band pass filtering, right, the signal we can represent it as actually what? X of t, right? After band pass filtering, we can represent the signal to be equal to X of t, right? This X of t will have signal component as well as noise component, right? So this white noise, if you remember, it has a power spectral density, double-sided power spectral density equal to n0 by 2, right? So this is SW of f, right? And when it is passed through a band pass filter, what will happen? Only the range of frequencies which is permitted by this filter, right? Only that part will be allowed, right? So the total power will be what? Area under the shaded region. All those things we have discussed, but again I told, right? So this X of t will have noise component as well as signal component, right? So initially we have to study what is see what is the input signal to noise ratio, so that you can measure either here or here, right? So anyhow, even though W of t is wide, it has all frequency contents, right? As our S of t has only these frequency contents, we have to consider the noise power falling within this frequency range. So you can either evaluate the inputs SNR or channel SNR either here or here. Both will be same, right? So this X of t is there. Then X of t we have to give to a, so this initially it's at the front end we are band pass filtering. Then we have to give it to a say coherent detector. Coherent detector, it will have a product modulator, right? It will have a product modulator, right? Product modulator, it takes two inputs, right? Two signals as input, right? So then, and the first one is X of t and the other one is actually what? A local oscillator, right? A local oscillator producing cos 2 pi fct, right? So here again for convenience we have assumed the local oscillator output amplitude is equal to unity, right? For simplicity, we have considered that, right? So then product model after product, what this product modulator does is actually what it multiplies x of t and this cos 2 pi fct. So when you multiply two trigonometric functions, you will get actually what sum and difference frequencies, right? All mostly some frequency will be falling in very high frequency range, and difference frequency will be in low pass range or low frequency range, right? So always please remember product modulator, what it does is it multiplies two signals. Mostly the signals we are modeling it as actually what trigonometric functions. So it will give sum and difference. So when you pass the resultant through a low pass filter, what we'll get is we'll get only the difference or whatever is falling within the DC range, that only we'll get. So we'll be passing it through a low pass filter. This low pass filter, right, its characteristics should be something like this, right? It will allow from minus W to plus W. Here again, we are assuming it to be an ideal low pass filter, right? So that if at all the message part in this, right? So we call this product modulator output as V of t, right? So that is low pass filter, and whatever we are getting at the output, that is, we'll call it Y of t. This is a say demodulated output. So the part which is shown in right this box is nothing but what the coherent detector part, right? So this is a system model, right? Now we have S of t, right? S of t is, again I'll write S of t is equal to C times AC cos 2 pi fct times m of t, right? Then this W of t, when passed through this band pass filter, right? Let us assume the noise output of the band pass filter is n of t, right? So this will be equal to S of t plus n of t, right? So this x of t, it is equal to S of t plus n of t, where n of t is actually what the band pass filtered W of t, right? N of t is band pass filtered W of t. You know what happens, right? When a white noise processes pass through an ideal band pass filter or low pass filter. We have seen that in last class, right? So this n of t, for convenience, what we'll be doing is we'll be representing this n of t, right? This n of t will be a band pass signal. N of t will be a band pass signal, right? So this n of t can be represented in canonical form as n I of t. This n I of t is in phase signal, right? And in phase component of n of t, n I of t cos 2 pi fct, then minus, right, minus n q of t sine 2 pi fct, right? So this ni of t is in phase signal and q of t is actually quadrature phase signal. So this is called actually what canonical representation of this. If n of t, it's actually what, it's a narrow band noise, right? N of t is a narrow band noise. Narrow band noise means it, right? Yeah, and it can be represented using its in phase. This n of t is in phase component ni of t, and quadrature nq of t is quadrature, right? Phase quadrature component, right? Q and q of t is quadrature component, right? So these are nothing but, if you remember the low pass equivalent, right? This low pass equivalent of a signal, ni of t and nq of t are nothing but what, the real and imaginary parts of that. I told, right? The detailed discussion of canonical representation is beyond the scope of our syllabus, and you will be studying it later. But please remember, this is equal to n I of t plus j n q of t, right? So if you right, revisit the video on Hilbert transform and complex low pass equivalent of a signal, all those things, there you can see this complex low pass equivalent. So this ni of t, it is real part of n tilde of t, that is complex low pass equivalent, and nq of t is imaginary part. This n tilde of t in turn is actually what? This is a narrow band. This is a band pass filter. This is a band pass signal, right? But this is actually what? The low pass equivalent. Low pass equivalent, right? So I'm not confusing you people. So what you should remember is only this result, right? This is what you have to remember. And this ni of t and nq of t, they will have same say spectral characteristics as that of n of t, right? Except for these are actually what? Low pass equivalents, right? Ni of t and nq of t, it will have same spectral character. If you pass Ni of t alone through a low pass filter of bandwidth, right? If you pass Ni of t alone through a low pass filter of bandwidth, right? 2W, right? LPF of this characteristics, right? Then you will, the output will be N0W, right? That's what you have to keep in mind, right? So okay, as and when required, we'll use it. So this is our N of t. So now what will be X of t? X of t will be C AC cos 2 pi FCT times M of t plus Ni of t cos 2 pi FCT minus NQ of t sin 2 pi FCT. I request everyone to take it down along with me, right? So this is X of t. Now, before we move ahead, what we can do is we can just evaluate, right? So what is the signal to noise ratio at this particular point or at this particular point, right? This X of t is nothing but what? S of t plus N of t, right? S of t is this. So the total power in X of t will be, the total power in X of t will be equal to power in signal, right? Plus power in noise, right? So here, for this, we can find what is the SNRI or SNRC, right? Input signal to noise ratio. We can also call it as actually what? Channel signal to noise ratio, right? So how to find that? So SNRC. This is nothing but what? Channel signal to noise ratio. That's what we are going to find now, right? Channel signal to noise ratio, this is equal to signal power at input divided by noise power at input. So when I say input, it can be before the band pass filter or even after the band pass filter. But before, if you are taking before the band pass filter, what you should consider, you don't have to consider the entire noise power for all frequencies. You have to consider only the range of frequencies which are of our interest, right? So what is the power of this particular signal? So there is a constant, right? There is a constant, and AC cos 2 pi FCT. This is our actually what? Carrier, and there is M of t, right? This M of t, right? We'll assume this M of t has a power equal to P watt, average power equal to P watts. This will be nothing but what? Integral minus infinity to infinity SW or SM of, right? SM of df. That is, if you integrate the power spectral density of M of t, you will get the average power. We are assuming it is already known. We are assuming the message power is equal to P, right? So this is some arbitrary message which we have considered, right? Which has a spectrum like this, right? A spectrum like this. We'll assume this has a power equal to P. Now what will be power of this carrier part? AC cos 2 pi FCT, its power will be equal to AC square by 2. Average power delivered to a 1 ohm resistor, that will be equal to AC square by 2. And the C is actually what? A constant part. So it will contribute as C square. So the total power, you can actually what? Multiply all these things. Power of this, if you're up, C means it's a constant. If you're applying a DC to any system, right, it will deliver a power corresponding to its square of magnitude, right? And AC cos 2 pi FCT will deliver a power corresponding to AC square by 2, and M of t will deliver a power corresponding to P. As you are multiplying these things, the corresponding power also should get multiplied. So this is equal to power. I'll just simply write the signal here. Power in C AC cos 2 pi FCT times M of t, right? Power in this divided by power in noise, right? Power in N of t, right? So this is equal to, right? So power in C AC cos 2 pi FCT M of t will be C square AC square by 2 times P divided by power in N of t, right? So N of t is nothing but what? I'll just draw it here. This noise having PSD equal to N naught by 2 pass through an ideal band pass filter at having bandwidth equal to, say, 2W, right? So having bandwidth equal to 2W. So it will be equal to N naught times 2W, right? So this power in N of t, it will be equal to N naught times 2W. That will be equal to N naught times 2W. So N naught by 2 times 2W, sorry, right? N naught by 2 times 2W. So that will be equal to, right, N naught by 2 times 2W. So that 2 and 2 will get cancelled. So that will be equal to N naught W. So this, I'll write it down, right? So now channel SNR, right? This is for DSBSC, channel SNR, right? SNR C for DSBSC, maybe I can write DSBSC. It is equal to, this is C square AC square P, this 2 and 2 gets cancelled, so this 2 comes to denominator, so it will be C square AC square P divided by N naught W. This is the channel SNR or input SNR in a DSBSC system, right? So right, now what we have to do is this. Now again we will go up and see what happened to this X of t, right? So this X of t has signal component and noise component. So if we do signal power by noise power, that will give us channel SNR or input SNR, right? The SNR of the signal before we provide to a demodulator, that is input SNR, right? So now that is being given to a product modulator. What the product modulator does, it gives out V of t by actually what? Multiplying X of t with cos 2 pi FCT. So that's what we have to do next, right? So the product modulator output V of t, right? Product modulator output V of t is equal to X of t times cos 2 pi FCT. This X of t is in turn actually what? S of t plus N of t times cos 2 pi FCT, right? And this S of t in turn, you know, is equal to C AC cos 2 pi FCT times M of t plus N of t is Ni of t cos 2 pi FCT minus NQ of t sine 2 pi FCT, right? This entire thing into cos 2 pi FCT, right? Now we can simplify here, right? You have actually what? CAC cos 2 pi. First term is this, right? Second term is Ni of t cos 2 pi FCT. Third term is NQ of t sine 2 pi FCT, right? So this first term we have a cos 2 pi FCT. So this cos 2 pi FCT and cos 2 pi FCT, it will be cos square 2 pi fct, cos square 2 pi fct, it is equal to what? 1 plus cos 4 pi fct all divided by 2, right? It is cos square theta is 1 plus cos 2 theta all divided by 2. So we can simplify it like that. Again, we have actually what? Ni of t cos 2 pi fct times cos 2 pi fct. This again will get a cos square 2 pi fct. That again will be what? Half plus cos 4 pi fct by 2. Then we have here sin 2 pi fct times cos 2 pi fct. What is sin theta cos theta? Sin theta cos theta, right? 2 sin theta cos theta is sin 2 theta. So this will be actually what? Half sin 2 theta, right? Half sin 2 theta. So if you apply all these results, and if you apply all these results, then we will get v of t to be equal to, right? I'll write, right? V of t to be equal to, are you able to take it down along with me, right? If not, please do feel free to, right, stop me, right? But these are simple, nothing is there, right? Shall I continue, or you want some time to take it down? Okay, I think I'll continue, right? So if you rearrange it, so what we'll get is we'll have a half c times ac times m of t term will be there. Then half, right, this ni of t term will be there, right? Then we will have plus half, we'll have this cos 4 pi fct terms, right? We have two cos 4 pi fct terms, so we can collect all those terms together. That will be c ac m of t, ac m of t plus ni of t times cos 4 pi fct, right? Then we have 1 minus half sin 4 pi fct term. So minus half nq of t sin 4 pi fct term. So what we have done is, only wherever we have cos square theta, we have replaced it with actually what? Half plus cos 2 theta by 2, right? And wherever we have sin theta cos theta, we have replaced it with half sin 2 theta, right? That's what we have done. This is our v of t. Now what is happening if you go back to our system model, right? This v of t, this product modulator output is given to a low pass filter, right? Product modulator output is given to a low pass filter, which will allow a frequency only up to w, right? So this v of t is applied to a low pass filter. So for our leg, whichever high frequency terms are there, whichever is having actually what? Frequency equal to 2fc, those things will be eliminated, right? Those things will be eliminated, and only the DC terms means wherever we have a constant in this expression, only those terms will survive at the output of low pass filter, right? So which are the low frequency terms here? So we have half c ac m of t, that is a low pass term, right? Why? Because its frequency, it's m of t by default, it's a low pass signal or band pass signal, baseband signal. So this is a low pass term. Then half ni of t, this is again a low pass signal. But if you see here in this, we have cos 4 pi fct. So this signal will be rejected by the LPF, and this term also will be rejected by the LPF. So what is left out is only here, right? Only this. So output of LPF is our y of t, right? Output of LPF is y of t. So LPF output, that is y of t, this will be equal to half c ac times m of t plus half ni of t, right? This is what is left out. This is our demodulated output, right? DSBSC signal, when we demodulate it using a coherent detector, this is what we are getting. So once again, I am telling, if you want to, right, if you don't want the C, right, if you want to take the system contribution, right? If you don't want to consider the system contribution, you can consider it as unity. You don't have to consider it, not a problem. In some textbook, they have not considered this constant, but I always think, right, maybe considering the dependence on the system, maybe we, even though we have this set of bandpass filter, right, or there can be some front-end amplifiers, all those things, that contribution can be what modeled using the C. Anyhow, whenever we are finding out this figure of merit, that C will get cancelled. You can see later, right? So this is a demodulated output or demodulated message signal, right? So you can see here we have our message term and a noise term. So initially the noise had in phase and quadrature phase component, right? So after passing it through a low pass filter, after after doing product modulation and passing it through a low pass filter, you can see the quadrature phase component is completely eliminated. That is an inherent actually what advantage of this coherent detector, right? This quadrature. So maybe we can now note down, right? So this one of the important property of coherent detector, right? So coherent detector, one of the important property is actually what? First one is quadrature phase component of noise is completely eliminated, right? Component of noise is completely eliminated, right? And this in phase component, right? You can see this in phase component is like it's additively what tampering or demodulated. It's not actually what getting multiplied. If it was getting multiplied or something like that, it would have been difficult, right? So as it is additive, right, it's easy for us. So second point is actually what? In phase component. I'll write it as Ni, right? In phase component of filtered noise, right? It is additively mutilating this message signal, right? And or I can tell message signal and in phase noise component appear additively at the receiver output, right? Ni and M of t appear additively, right? I can write like that at receiver output. So this is actually what a very important property of coherent detector, which makes it different from other say type of detectors. If instead of this, if you were using an envelope detector, right, this wouldn't have been the case, right? And one more thing, these two things what I mentioned, it is irrespective of input SNR, right? Whatever be the input SNR or channel SNR, right? Quadrature phase component of noise is completely removed, and in phase component of noise and M of t will appear additively at the receiver output, right? So now this is our output. Now what we have to do is, here you can see here we have a signal component or message component, right? And we have a noise component. So now we can find signal to noise ratio at the output. SNR O we can find, right? Signal to noise ratio at the output. Signal to noise ratio at the output, it will be equal to, you can say, power in, right? So I'll write it is half C AC M of t. This is our signal component, power in half C AC M of t divided by power in half Ni of t, right? Power in half Ni of t. So I told, if we have product of, right, constants and different signals, what we should do is these constants will it will contribute average power of proportional to square of its amplitude. So we have half, so it will contribute actually what, half square. C square, AC will be AC square, and M of t we already know its power is equal to P, right? AC it will be AC square, C will be C square, half will be half square. So similarly here we have half, this half will contribute actually what, as half square. Then this, as I told, this Ni of t, right? Please remember, right? Both Ni of t and Nq of t has same spectral characteristics as N of t. So please don't think as N of t is obtained as sum of actually Ni of t cos 2 pi fct and Nq of t sin 2 pi fct, right? This N of t, Ni of t and Nq of t, it has same spectral characteristics. So it has same power spectral density, right? So the power spectral density will be like this only, N0 by 2, right? If it is Ni of t or Nq of t or N of t, the power spectral density will be same. The only difference is actually what, this N of t, N of t is a narrow band pass signal. These two are low pass signal, right? So for instance, N of t will have spectral characteristics like this, right? N0 by 2, which is centered at Fc and minus Fc. But this Ni of t and Nq of t will have a low pass characteristics. But the total bandwidth is equal to what? 2W, right? Total bandwidth will be equal to 2W. So this Ni of t will have power equal to what? N0 W. Ni of t will have power equal to, say, it will have twice N0 W. Ni of t will have power which will be equal to twice N0 W. So this is N0 by 2, and this is W, and this is W, right? So it will have a power, no, average output power that is equal to twice N0 W. So the total I can write now, right? So the power in this signal is equal to, say, C square AC square P, and there is a 1 by 2 square, it is equal to by 4 divided by, and the signal here, this will be equal to 1 by 4 times 2 N0 W, 1 by 4 times 2 N0 W, right? 1 by 4 times, so it will be 1 by 2 N0 W. So if you simplify it, what we will get is SNR at the output, that is equal to C square AC square P divided by 2 W N0, right? C square AC square P divided by 2 W N0. So this is our SNR at the output, right? SNR at the output. Now we have to find what is the figure of merit, right? So we have to find what is the figure of merit, right? So to find figure of merit, right, or FOM, or we can also write gamma, right? This gamma is equal to SNR at output, right? SNR at output divided by SNR at input, or channel SNR, right? So this will be equal to SNR at output is actually what, C square AC square P divided by 2W N0, right? This entire thing divided by what was SNR at channel? Can anyone tell me? Right, we have already written this, right? Can anyone tell me what is SNR C in channel? Yeah, you can either type it in or unmute and tell. Maybe I'll call someone. Um, Ritual. What is channel SNR? SNR at channel SNRC. You can either type it in or unmute and tell. Right. Now if I may request you to unmute, right? Please unmute and tell. We already did it. We already found it. Right. So I am expecting all of you are taking it down along with me. Yeah. Tell me. Rajul, please unmute and tell.
C square,
C square. One second. I'll write it down.
C square,
Right. C
AC
square.
square, P by 2,
C square. Sorry. AC square P
P
by
by 2,
2
by
again
N not
W
W.
and no, right. So both are same. So what we get is for DSBSC the figure of merit, that is SNR at the output of receiver divided by SNR at the input of. Thank you, Prajwal. Right. This is equal to, this is same. So this is equal to 1. Right. This figure of merit is 1. Right. For DSBSC. So for DSBSC, output SNR is equal to what? Channel SNR. So it's not, it's the receiver is not say worsening the condition. It's not reducing the signal to noise ratio. Basically what we need is we should have, right, SNR should be as high as possible. Why? Or the signal power should be greater compared to noise power. So SNR will be greater than 1 normally, right? So and the channel SNR and output SNR are same, means at the input the ratio of signal to noise power is same as the signal to noise power ratio at output, right? Which means it's not further worsen the situation, like it's maintaining the SNR what is there at the input as such at the output as well. So this is okay, right? Permissible. But if it was less than 1, right, that it's not that right favorable condition, right? So normally we need it's greater than or equal to 1. This form figure of merit should normally be greater than or equal to 1, but it's equal to 1 here. That is okay. So this is the figure of merit of DSBSC. Next, what we'll do is we'll try and find out the figure of merit of standard AM, right? So, but for standard AM, right, we are not using this coherent detector. We'll be using an envelope detector, normal envelope detector. But the problem with standard AM is it has, and we are redundantly transmitting the carrier power, right? So a carrier is not suppressed. Carrier power is redundantly being transmitted for the sake of simplicity of the receiver, right? For the sake of simplicity of transmitter and receiver, we are transmitting carrier power, right? So that's what we're going to do next. So before that, we'll have a quick recap what we have done, right? We have considered a system model, a DSBSC receiver. It had a band pass filter and a coherent detector, right? Then we found the noise we modeled as additive white Gaussian noise process, right? Where white noise means it has all frequency component. So the power spectral density is equal to N0 by 2 for all frequencies. It's a double side power spectral density, right? Then it has a 0 mean value. And then we considered S of t to be equal to AC cos 2 pi fct times M of t, where we assumed initially itself this M of t has an average power equal to P, right? And then we found the input or channel SNR as C square AC square P by 2 AC square by P by 2 W N naught, and then we pass this S of t through a product modulator. Then we got X of t. X of t had two components, S of t and N of t, right? Then that is passed through a low pass filter, right? So then we expanded that S of t plus N of t, right? So what we did is we did some rearrangement. Wherever we had this cos square theta term, we replaced it with 1 plus cos 2 theta by 2. Wherever we had this cos theta sin theta term, we replaced it with half sine 2 theta, right? Then when we rearrange, when we pass it through a low pass filter, we could see all the high frequency components were getting filtered out, right? And what we got is we had an M of t term and half Ni of t term. So we found this M of t and in phase component of the filtered noise output are appearing additively at the receiver output, and quadrature phase component is completely eliminated. That we mentioned as one of the important advantages of properties of coherent detection compared to other mode of detection, right? So then what we have done is we only the DC terms or the low pass terms were left out. Not DC, the low pass terms were left out. So we found the output SNR, right? Output SNR is output SNR will be equal to C square AC square P by 2 W N naught, right? Then when we found the figure of merit, right, we were getting it to be equal to 1. So that is what we have done. So now we are telling figure of merit of DSBSC is equal to 1. So later on, like in next derivation, we'll prove figure of merit of standard AM, right? So similarly, this is DSBSC, right? So now further we'll prove figure of merit of standard AM, right? Oh, I'll write only AM for standard AM. This will be equal to, so we'll get it is equal to Ka square P divided by 1 plus Ka square P. So you can see this is less than 1, right? This is less than 1. Why? The main reason is the presence of carrier, right? We are wasting, right, power by transmitting carrier. That the only advantage of transmitting carrier along with the this modulated upper and lower side bands is that the receiver and transmitter complexity will be less, but this carrier as such it does not carry any information, right? It does not carry any information. So the power which is there in carrier will not actually contribute to the signal information part of the signal. So that's why the figure of merit of AM, right, it is Ka square P divided by 1 plus Ka square P, that is less than 1, right? Then maybe we will do a problem of finding figure of merit of a single tone modulated signal. Then we'll do figure of merit of SSB, and then we'll move on to actually figure this noise in FM, right? So maybe it's already 12:25. We don't have time to discuss the noise in AM, so that we'll do in next class. So what I do is I request all of you to I hope all of you have taken it down, right? So I request all of you to go through it so that maybe the noise in AM and SSB I can just rush through. I don't have to spend much time on that, right? Okay, so with that note, if you have any doubt, please feel free to ask. Right? If you have any doubt, please feel free to ask. Yeah. Someone has typed in something. So how it is 0.5, Sherwin? Okay, you have typed, you got it, right? You got it, right? Right. So one thing, maybe what I feel is normally you used to get confused is, right, this input signal to noise ratio, right? Input signal to noise ratio while you are evaluating, right? So maybe what you can do is you don't have to consider after the band pass filter, you can consider before the band pass filter, right? Input signal to noise ratio, you can consider it before the band pass filter, right? you are evaluating channel signal to noise ratio before the band pass filter. So the noise power will be N naught W. Right here, the noise power will be equal to N naught W. Right, before the band pass filter, right? But when we pass it through band pass filter, right, and at the end when we are evaluating the noise power of Ni of t, right, noise power of Ni of t, this is equal to, right, N naught times 2W, right? So these two things you have to remember, right? So I should have, right, I don't think, right, this detailed discussion of uh, canonical representation and narrowband noise is required. If you can just, right, remember these things, right? Here, while evaluating input signal to noise ratio, the noise power input is actually what N naught W, what we considered, and the noise power output is equal to what, twice N naught W, right? So please do keep that in mind, right? Only that is the point where you may, right, make some mistake. Otherwise, everything else is straightforward, right? And any doubt is there? Any other? No. So okay, now please feel free, right? How many of you got an idea on how to analyze a continuous modulation system for noise? How to find the fig, say figure of merit, right? Please feel free, right? If uh, 20, okay, thank you for responding, right? Then right, so why, and one more thing, these derivations, as these are derivations, I what I prefer is, instead of using PPT, if I'm writing it, maybe you will be able to what, write it along with me and practice. If I'm using PPT, then it will be like, right, uh, you may not, right, I may not be waiting for you to what, take down. Of course, right, these things are, these derivations are there in the notes which I have given. You can refer that also, right? But as usual, right, I'm sticking to the notations and the procedure which is followed in your prescribed textbook, right? Other ways are also there. I'm not telling those are wrong, but they are using slightly different notations. For instance, if you like consider the local or the textbook, right, they have not considered the system constant C, but that also won't be a problem. But in between, the results won't have C square, but the final figure of merit value, it has to be equal to 1. That's what you have to keep in mind. So these things, right, we have different conventions and different textbooks are using different right approaches, but that is not a problem, right? You can stick to this. If you understand this, and if you, right, if you are able to follow this, I would recommend you to what, uh, follow this. Otherwise, you can actually what, switch for the other, the whichever notes I have given, it has these things, but maybe in slightly different way. Some maybe and one more difference is, instead of Ni of t and Nq of t, some other local other textbooks, they may be using Ns of t and Nq of t, or Ns of t and Nk of t, right? That also is fine, as long as you are able to appreciate these things. Any material you are referring, I don't have any problem, but try to stick on to the notations in your, right, the procedures in your prescribed textbook, right? So right, let us assume, as normally what happens is in sorry